Hello and welcome back. In this video, I want to begin a new topic, and that is the relationship between work and energy. But before we get too far into this discussion, I want to first explain why it is important that we study energy. So some of you may be thinking, well, we have Newton's laws, so can't we just use Newton's laws to solve any problem? And for the most part, in classical mechanics, you can use Newton's laws to solve any problem that you see. However, there are a lot of problems that are very difficult to solve using Newton's laws. So a simple example of this is the simple pendulum, which we studied when we talked about harmonic motion. So this is a mass that's hanging from a string. And if we go ahead and draw a free body diagram on this, we have the force due to gravity that points down, and then the tension force from the string. And if we think about this, the component of my gravitational force that's pointing in the direction of my motion changes as the mass moves. So for example, if I start out up here at 90 degrees, I have the string is over here at 90 degrees, and the mass is at the end of it, so my force due to gravity points vertically down like this. And this is the same direction that the mass is going to travel in when the mass is released. So the mass is going to swing down like this, so the force due to gravity is in the direction of the motion. However, when the mass reaches the bottom of its motion, the force due to gravity is going to point perpendicular to the direction of the motion. So when I'm down here, the force due to gravity points down, but the motion would point to the right. So if I swing down when I'm at the bottom, I'm moving now to the right, but my force due to gravity points down. So what this means is the component of my gravitational force that's causing the mass to speed up is going to change as the mass swings. So initially, all of the gravitational force is pulling the mass down, it's causing the mass to accelerate, but when I'm at the bottom of the motion, the gravitational force is perpendicular to the direction I'm moving, so it's not actually causing the mass to speed up or slow down. In addition to this, if we're going to apply Newton's second law, we also have to worry about the tension, and the tension is going to do all sorts of things as well. So for example, when the mass swings down to the bottom, when it's down here, the mass is moving faster, so the tension is going to be greater because it has to supply the centripetal acceleration. And remember that the faster the object moves, the larger the centripetal acceleration. Also, there's a component due to gravity that's pulling on the string, and the tension has to compensate for that. So when the mass is here at 90 degrees, the force due to gravity is perpendicular to the tension. But when the mass is down here, the tension has to pull up, and it not only has to compensate the force due to gravity, it also has to supply the centripetal acceleration. So the tension's always changing, the component of the gravitational force that causes the mass to accelerate is always changing. So this is a very difficult problem to solve using Newton's second law. However, it's very easy to solve this problem using energy. So whenever a force is applied to an object, and that object moves in response to that force, work is being done. And the formula for the work is the dot product between the force and the displacement. So remember, this is the dot product. We talked about this at the beginning of the year, and I said you don't have to know the formula for the dot product. So I'll show you several other ways that we could write this equation. Another thing I want to point out about this equation is I'm using delta r here to represent the displacement. So this is the change in the position of the object. The reason I use r to represent displacement is that this is the symbol that is used in the equation sheet that you have for your tests and on the AP exam. So the people who wrote the AP exam, that's the symbol they decided to use to describe displacement. So that's what I'm going to use as well, so that hopefully that'll be familiar to you when you're taking the test. So there are several ways we can write a dot product. One way is I could say that this is the component of my force that is parallel to my displacement times the displacement. Another way I could write this is I can say this is the magnitude of my force times the component of my displacement that's parallel to my force. Or I can say this is the magnitude of the force times the magnitude of the displacement times cosine of the angle between the force and the displacement vectors. So this equation right here, this last one, is the one that appears in the equation sheet. But at different times I'll use all three of these formulas, so it's a good idea to know all three of them. I should point out this notation down here, this is the same type of notation I used when I talked about torque. Right, so when I talked about torque, I said torque was the component of the force that's perpendicular to the lever arm times the lever arm. So I use a little subscript with a perpendicular sign Here I use a little subscript with a parallel sign. So this means the component of my force that's parallel to r. And this is the component of my displacement that's parallel to the force. So one important concept to understand about work is that work will only occur when a force is being applied and the object moves in response to that force. Okay? So what this means is that if you're standing somewhere and say you're just holding a box, okay, well, it definitely, it requires energy to just sit there and hold the box. It's going to tire you to do that. You don't actually do any work when you hold a box, okay, because the box is not being moved. The object doesn't have any displacement, okay? But if you were, for example, to pick a box up off of the ground and lift it, then you'll be doing work because you'll be applying a force and you'll be lifting the object, so there will be a displacement. Another thing I should point out about work is that we talk about work, there are two different signs. You could have positive work and you could have negative work. In general, when a force is applying to an object and is pushing it in the same direction of its motion, then the object tends to speed up, and we call that work a positive work. And when a force tends to oppose the motion of the object, we call this negative work. Okay? So when a force just all by itself, if it were to tend to cause the object to speed up, it's positive work. If the force all by itself would tend to cause the object to slow down, it's negative work. Now, I also want to go ahead and look at the units of work. So remember that anytime we have an equation, units have to be the same on both sides of the equal sign. So this means the units of work have to be equal to the units of force times the units of displacement. Recall the units of force are newtons, and the units of displacement are meters. So we see the units of work are newtons times meters, and we call this combination joules. So the units of work are joules. Now I do want to make one side note here. When we talked about torque, we found that the units of torque were also equal to newtons times meters. But when we talk about torque, we call the units of torques Newton meters. We don't use joules to describe torque. Okay? Joules are something that we use to describe work and energy. So even though the units of work are the same as the units of torque, we call the units of work joules, and we call the units of torque Newton meters. The reason for this is that if I apply a torque to an object and the object rotates, then that torque does work. And it turns out the work that's done by a torque is equal to the torque times the angle that the object is rotated through. Now remember that angles don't have any units, so this thing is just going to have the units of torque. So this thing, the work that's done by a torque, is going to have units of Newton meters, the same as the units of torque. And when we calculate the work that's done by a torque, then we would call this joules. Okay? So joules are a unit that's reserved for work and energy. So when we talk about torque, we still call it Newton meters, but when we talk about work, even though the units are still going to be Newton meters, we call them joules. So let's go ahead and look at a couple of examples. The first example says, a cable lifts a 1200 kilogram elevator at a constant velocity. The elevator moves 35 meters upwards during this time. And the question asks us to find the work that is done by the tension in the cable and the work that's done by gravity. So let me go ahead and open up a blank screen here. And let me first draw a little picture of what's going on. So there are two forces that are acting on the elevator. There's the force due to gravity, and that points down. And then there's the tension that points up. And when I do these problems involving work, I'll also go ahead and show an arrow showing the displacement. So the object in this case is going to move upwards. And what we were given was we were told the mass of the elevator is 1200 kilograms. And we were told that the object is going to move upwards 25 meters. And we were asked to find the work that's done by the tension and the work that's done by gravity. So remember, there's a lot of different formulas we can use to calculate work. One way we could calculate the work done by the tension is it's the tension force times the magnitude of the displacement, which in this case is delta y, times cosine of the angle in between them. So if we look at this, the tension force points vertically upwards, and my displacement is vertically upwards. So the angle between those two vectors is 0 degrees, and cosine of 0 degrees is 1. So my work is just going to be tension times displacement. So tension, another thing I should have should have done already. So if the elevator is moving vertically upwards at a constant speed, then Newton's second law tells me that the sum of the forces acting on the object is going to be 0 newtons, right? Because the object's not accelerating if it's moving at a constant speed. So if the net force acting on this elevator is 0, then that means the tension has to equal the force due to gravity. So my tension is just the force due to gravity, so it's mg, and then I got to multiply this by delta y to calculate the work. So now if I plug all this into a calculator, I have 1200 kilograms times 9.8 meters per second squared times 25 meters. I see that the work that's done by the tension is 2.94 times 10 to the 5th joules. Notice that this work is positive. There's a few reasons the work was positive. This really came about because cosine of 0 is 1. But conceptually, we can think of this as the tension is pulling the elevator upwards, and that's the same as the direction as the elevator's displacement, right? So the tension is what's causing the motion. It's pulling in the same direction as the elevator's motion. So the work that's done by the tension will be positive. Now let's calculate the work that's done by gravity. So this is the force due to gravity times the displacement times cosine of the angle between these two vectors. So if we look at this, the force due to gravity points down and the displacement points up. So let me kind of draw these two things. So we've got the force due to gravity, that's down, and we've got the displacement, and that's going upwards. So the angle between these two vectors, if we think about this, like, so if I rotated this by 180 degrees, they would point in the same direction, right? So the angle between these two things is 180 degrees. So we have cosine of 180 degrees. And it turns out the cosine of 180 is minus 1. So this is going to be minus mg delta y. Notice that that's just minus the work that's done by the tension. So this will be minus 2.94 times 10 to the 5th joules. Again, notice that the work is going to be negative. Now this happened because cosine of 180 degrees is minus 1, but we can conceptually understand this because the force due to gravity is opposing the motion of the elevator. So it's just by itself, it would tend to slow the upward motion of the elevator. So let's go ahead and look at another example. This example asks us to calculate the work that's done by the gravitational force on the moon when the moon orbits the Earth. So remember that work is equal to, there's a lot of different ways we could calculate this. One is that it's equal to the gravitational force times the displacement times cosine of the angle in between these two things. Notice the gravitational force is always perpendicular to the displacement, right? If the moon has a circular orbit, then at this point my displacement points vertically upwards, the gravitational force points like this. If, for example, the moon's up here, the displacement, like my velocity at this point, would point over like this, and the gravitational force points down. So the gravitational force and the displacement are always at 90 degrees. So what this means is the cosine is always cosine of 90 degrees. So the work that's done by the gravitational force of the Earth on the moon is always 0. And this is because the gravitational force is always perpendicular to the motion of the moon. So let's go ahead and look at one last example. This example says a 10 kilogram stone is thrown by a physics student off the edge of a 10-meter cliff. How much work is done by gravity when the stone is thrown vertically upwards, vertically downwards, or horizontally? And this is a really good example because it really shows why work is so useful, how it's very, very easy to calculate work in all three of these examples. So here we've got the stone that's thrown up, so it'll come up and then come back down. Here the stone is thrown vertically down, here it's thrown horizontally. We can see the path that the stone takes in each of these examples is very different. However, what we'll see is that the work is going to be the same. So let me go ahead and write down the known values. So the stone is 10 kilograms, and we're going to throw this off of a building that's 10 meters tall. And we're asked to calculate the work that's being done. So let's consider a couple of examples. So when the stone is being thrown vertically upwards, so the stone's going to come up like this, and it's going to come back down. So if I draw my displacement, right, the displacement points from the initial position to the final position, so the displacement looks a little bit something like this. So this is delta R. Now if the stone is thrown horizontally off of the building, then the path the stone takes is going to look something like this. It's going to travel outwards like this and then come down. So the displacement vector in this case is going to look something like this. It's going to kind of come out like this. I did not draw that very well. It's going to come out like this. So this is my displacement vector. Now, remember, there's a lot of different ways we could calculate the work. One way we can calculate the work that's being done by gravity is it's equal to the gravitational force times the component of my displacement that's parallel to the force. Okay? Now, if we look at these two displacements, right, the component of the displacement that's parallel to the gravitational force, that's the component of my displacement that's in the up and down direction, because gravity always points downwards. Right? The force due to gravity in both of these cases points down. So the component of the displacement that's parallel to this is the component that points down. So we have a component of the displacement that goes down and a component of the displacement that goes horizontally. That's the same thing for this one here. It's the component that's down, and technically there's no component horizontally if you throw the stone perfectly upwards. So what we see is that the component of delta R that points parallel to G, that's this component right here, it's always the same, right? If the stone is thrown off a 10-meter cliff, the stone always travels downwards 10 meters before it hits the ground. And it's that component of the displacement that's parallel to the gravitational force. So what we see is that no matter how the stone is thrown off the building, because it always moves 10 meters downwards, and that's the motion that's parallel to the gravitational force, the work is always the force due to gravity, which is mg, times the change in the height. So here we have 10 kilograms times 9.8 meters per second squared times 10 meters. So this is just equal to 980 joules. So it doesn't matter how the stone's thrown from the cliff, 980 joules of work will be done by the gravitational force. So for example here, when the stone's thrown vertically upwards, when the stone travels upwards, gravity is pointing in the opposite direction of the stone's motion. So when the stone is thrown upwards, gravity initially does negative work on the stone. When the stone reaches the top of its trajectory, it starts to come back down. And when the stone starts to come back down, gravity is doing positive work on the stone, because the stone's moving down and gravity points down. So it turns out by the time the stone returns back to its initial height, the net work that's been done by gravity is zero. It did negative work when the stone came up, it did positive work when the stone came down, and by the time the stone returns to its initial height, the net work that was done by gravity is zero. So from this point down, gravity does positive work, and it's the same amount of work that gravity does on the stone if the stone were thrown, for example, say horizontally off of the cliff. So it's the same amount of work in all three cases. So at this point, I think I'd like to end this video, and in the next video, I want to talk about kinetic energy and the relationship between work and kinetic energy.